Good afternoon. We can start our lecture on elasticity. Today I would like to talk about iterative procedure for studying stability. So solving the not traditional eigenproblem associated to this stability of aircraft. And initially we study as a first methodology the PK method, like here. And today we essentially consider this couple of method, the PK method, and the second one, the K method. And we started last time presenting the PK method, which allows to evaluate poles and also eigenvector, but the key point is the determination of poles, because the eigenvectors evaluation is just a standard resolution of an homogeneous algebraic system. So the main difficulty is on evaluating the poles of the system. And by using the PK method, one is able to evaluate all the poles of the system whenever one has fixed the flight parameter, like the density, the speed, the velocity speed U infinite, and the Mach number. Up to now, we developed a theory for a compressible flow, and therefore we have not considered compressible unsteady flow, but only uncompressible, and therefore the Mach number is not at the moment a parameter. And the second method, the K method, which I want to consider today in our discussion, is an approach, is a method which is able to identify only the critical condition for our system. Okay, so this is the main differences between the PK and K method. So in the PK method, we introduce some approximation. In particular, we assume to evaluate the aerodynamic metrics only in the imaginary axis. And this is an approximation, of course, and this approximation is true, is negligible whenever the poles are close to the imaginary axis. Then we have essentially consider the aerodynamic part as independent by the frequency, in the sense that we will not consider the relationship between the aerodynamic omega dependency with the fact that that dependency on omega, or on the plus variable, is exactly the same dependency of the rest of the system, including the inertial force, like this here. So this S, for example, this S here is not different, but with respect to this S here, but we separated this dependency in artificial way just to implement our continuation method approach, just like here in founding the root of a standard equation. So at the end of the story, we have a system with a matrix A, a state matrix A, which is artificially depending on K, the user frequency, and therefore we have a matrix for any K fixed. and therefore this is the basis of the iteration. And we fix, for example, the flight parameters, and then first of all we check if we have a static stability, like a divergence. If not, then we can start the procedure for finding the poles of the system, and then we assume a value for the diffusive frequency just inspired by the structural pole. So we give as initial guess a diffusive frequency as equal to the structural first natural frequency multiplied by L and divided by U, and it is initial guess for evaluating A, and then we evaluate the eigenvector of A. So we have a set of poles after this standard eigenproblem, which are not at all the pole of the system, but we have to check that if one of these has an imaginary part such that this quantity be the initial guess we gave for K. If yes, we have just finished and we have found a pole. If not, we have to iterate the process, and we have to consider the new evaluated poles, then evaluate another K and go ahead up to a convergence. And after this convergence, we have a set of the poles of our system, and then we can modify the parameter for rho, U infinite, and Mach eventually for defining another set of eigenvalues S. And so this is a way for evaluating the root locus. For example, if you froze the density and the Mach number, you can variate the velocity, the U infinite, and then we may have a root locus with respect to U. Another typical representation of the poles, this is the standard root locus representation here, but we may have also this classic VG plot. And in a VG plot, if you find for example, on site, the word VG plot, you probably find something interesting. For example, V plot. Yes, you have thousand of VG plot like this. This is the velocity and the damping. And for example, this is another VG plot, another VG plot. This is standard. It is standard in aeronautical flutter stability studios, and I want to show if there is something interesting in terms of. It's not easy to find a public VG plot for aircraft because the company has essentially declaring to you the stability of the aircraft essentially. So it's not easy to find public VG plot on site. Let me plot, for example, Airbus. Yes. Here maybe we have something. And oh, excuse me. Yes, please. Okay. It's not easy to. Okay. So this is, for example, the statistical loss data for Airbus A320, and if you will find, probably here we have something on VG plot. Okay. Data criterion, flap, flight loss, Venn diagram. I remember to find something about the VG. Okay. Gas vertical load factor data. No. However, I will find it, and I will show you this plot for some application. And the standard presentation is something like this. Look, for example, we have this. This is a VG plot. You have the true high-speed foot per second, for example, here, and you have the mode 1, 2, 3, 4, 5, 6. These 10 are essentially the 10 poles of your eigenproblem, and on the axis, x-axis here, you have the true airspeed. In this case, true is in the sense of aeronautical language, the sense that is the equivalent velocity. And you can see here that this red curve here, which is currently the 4 mode, is the critical one, because just here you have a crossing of the x-axis, which is representing the velocity, and you can see that the 4th mode is the critical one. And corresponding here, you have the frequency, we have the imaginary part variating, and this part is exactly this representation in real and imaginary part is quite equivalent to plot your root locus here. Okay, so you have velocity, and in the ordinate you have the real part of the real part of the poles and the imaginary part of the pole. Now, typically, what is intended by G is not probably the real part, but it is the ratio. Typically, G is typically a damping coefficient, and then it's not the real part of the poles, but it is typically the ratio between the real part and the imaginary part. And this is something similar to what happens in the standard damped vibration of elastic system. You have a response with an envelope. For the free response of a damped oscillator, you have that the envelope is something like e to the minus g or zeta omega n t multiplied by the cosine of omega t plus a phase, blah blah blah, and then you have that the real part is g by omega n, and therefore g is the ratio between the real part and the imaginary part, which is omega n. Okay, so this g is something relevant in vibration, because what is important in vibration is not the absolute value of the real part of the poles, but which is important is the ratio between this evaluation and the imaginary part. Because what you want to measure is the number of oscillations you can see before the response is totally damped out. Okay, so it's not important the absolute value of this exponential curve, but the role of this exponential curve with respect to the frequency of the oscillation. And this is the meaning of G. Okay? And so here we have G plot. So we have the ratio between the real part and the imaginary part. And here I have represented the critical curve here with our flatter critical value. So what I expect in future on your report is something like that, representing your Bougie plot in your analysis. Okay. Now I want to talk about the other procedure, the key method. The K method is another type of K method. K method. It's also known as the American method. And in this method, only the margin stability are evaluated. Margin means the flutter frequency and the flutter speed if you fix the density, for example. Density fixed, and of course Mach number fixed. You may evaluate these two parameters. So you want to evaluate only the crossing pole. So you want to evaluate this omega flutter and the value of the parameter u flutter, flutter speed. So this omega and this u flutter are also determined by your reduced frequency critical value, which is defined like omega flutter by B, reference length, half chord, divided by U flutter. Okay? So, how can we evaluate how these two quantities may be evaluated in an iterative process? Okay, the starting point is always the flutter equation. So we have initially something like this. Now I only want to include a damping matrix, structural matrix. Structural damping. And I have I want to include a stiffness, and in our flutter equation you have S and U, and this equation are referred to an eigenvector W, a complex eigenvector W. Now, in the margin condition, remember when we studied the panel flutter, we wanted to study only the stability margin, and then if you want to study the margin, you can set S equal to J omega. And therefore you want directly find your research along the imaginary axis. So walking just here along this axis. Reduce our equation here. And so we have that minus omega square mass matrix. This is a model mass matrix, do not forget this. And this is the plus J omega D, the structure damping. We have a stiffness minus QD E omega, and we want to refer this to our eigenvector. Now, in this procedure, we introduce, this is a new way for implement a, a process, an iterative process, like the continuation method. In order to implement this iteration process, we introduce an artificial parameter. Artificial means it does not exist. So this parameter will be cancelled at the end of the iterative procedure. So an artificial parameter G as hysteretic damping. So we want to consider here this artificial parameter in this way: 1 plus G by I. You know that this is something like damping, but this is a strange and also a wrong damping, because this is the unit, the imaginary unit. So let me use J, not I, for consistency. J. This is the artificial hysteretic damping. Okay. Okay. Now we can recast our equation in a suitable way. We have to satisfy this flutter equation, and we can consider the aerodynamic matrix as a master. Note that in the PK approach here, we consider the aerodynamic matrix in real and imaginary part as stiffness and damping term. In particular, we include the real part as a stiffness, and the imaginary part as a damping. As you can see here, you have the real part together with the stiffness, and you have the imaginary part here in the damping partition of our matrix here. But now we want to consider the aerodynamic as a mass term like this, and therefore in this approach we write minus omega square by m, and then we write minus dynamic pressure divided by omega square in order to respect this, and E, and we want to see the aerodynamic term as a function of K. So I want to collapse these two dependency, like depending on K. Imagine that this K is separated by the rest of the dynamic. Of course, this is false. This is not true, but we want to assume this in order to implement our procedure. And at the end, we want to converge. And so this is a global mass term. And next, we have this damping, structural damping term, and this strange viscous term, artificial viscous term, like this, with this G. Okay? Now, I want to, if we want to write W tilde, it's okay for the eigenvector, just to emphasize that this eigenvector should be complex eigenvector. Now, what can we do? We want to divide this equation by I plus jg, so divide 1 plus jg, so this is 1 plus jg, and then 1 plus jg. And I want to define a new complex variable, p, which is equal to j omega divided by square root of 1 plus jg. And so this is p1, and so p1 square is exactly equal to minus omega square divided by 1 plus jg. Okay, so here I have p to the power 2, p1, excuse me, to the power 2, and here I have 1, and here I should have this by this, and therefore this is p1, but since at the end of the iteration process we will have g equal to 0, I neglect this term and I only preserve as final equation the following equation, in particular this equation here. I only consider this p1 to the power 2 by m minus, and look, we have omega square, and therefore if you consider this qd like 1/2 rho by u infinite, instead of this, you have that this omega square multiplied and divided by b square should give a reduced frequency here, like this. You have a reduced frequency here, like this. This is k square, and so we have the following: minus 1/2 rho b square e evaluated at the reduced frequency divided k square, and then we have plus p1 by d plus kappa, and then w equal to 0. So, as you can see, we have apparently a standard characteristic equation in P1, unknown. But in the reality, P1 is, of course, related to omega, it's related to k, so, of course, this equation is not closed. Okay, it's not closed, but it's an open equation in the sense that you have a parametric dependency on k, but your P1 unknown is also depending on k as well. Okay, therefore, we have to organize our iteration in this way. We can, once k is fixed, one can evaluate in standard way, P1 or P1 to the power 2. Now know that P1 to the power 2 is P1 to the power 2, this is P1. P1 on the power 2 is minus omega squared divided by 1 plus jg. So, look, P1 to the power 2 is equal to minus omega squared divided by 1 plus jg. And so you have minus omega squared 1 minus jg divided by 1 plus g to the power 2. Of course, I have multiplied numerator and denominator by 1 minus jg, numerator and denominator. Okay, and so here we have separated the real and imaginary part of P1 square. We have a real part like minus omega by 1 plus g square plus j, an imaginary part given by g omega square divided by 1 plus g square. So, at the end of our story, we can do the following plot. Reduce the frequency, and you can plot, for example, the imaginary part of P1 square. You fix this k value, and you can evaluate P1 or P1 square. So for each k, you can do an evaluation of this imaginary part. You should have something like this. And correspondingly, you have the real part here. And in the real part, you have something like this. And of course, you have many of these curves. You have a curve for any value of P1. Many curves, because you have developing this determinant equal to 0. Let me rewrite this, please, just to be clear. This is the equation to be developed: determinant P1 square mass matrix plus 1/2 rho B square E k divided by k square, and plus dp1 plus k, determinant equal to 0. So by this equation, you evaluate P1 square. You have many P1 square, many curves. We plotted only one for the sake of clarity. We plotted only one. So here, for you imagine to have this, and focus your attention on this point here, on the crossing here. You can evaluate this point here, and in this case, you have satisfied here one. I don't like too many red color. Here, one has satisfied the characteristic equation, because we have solved the determinant equal to the characteristic equation, and you satisfy also one satisfy also 0 equal to imaginary part of P1 square, which means, look here, which means G equal to 0. Because here you have omega not equal to 0. So if you have an imaginary part 0, you have necessarily G equal to 0. And G has to be 0 because it's an artificial parameter. Okay? So this is the flatter margin condition. But what about our flatter parameter to be evaluated? Okay, so we have a reduced frequency here. This value is K flatter. So we have found K flatter. We found K flatter as value here determined, and K flatter is omega flatter by B length of reference divided by U infinite U flatter. Okay, and therefore if you have this and you have also a real part here, omega, here you have that the real part here that you have determined flatter is equal to minus omega flatter to the power 2. So we have identified this, we have identified this, and therefore we have identified U infinite flatter, U flatter, as equal to K flatter, excuse me, you have U flatter is equal to omega flatter by B divided by K flatter. It's trivial, okay? So we identify by this curve. Of course, you have many of this. Okay, but if you could have this, another one, another one with the related curve, imaginary. So you can evaluate all this curve and you find the lower value of flatter velocity evaluated. You don't care about higher value of U critical velocity. You are interested to the first one, to the lower one, as you can imagine. Okay. And so we have this with this related curve. For example, imaginary part on another of this pole, you have one, you have second, or the other. Okay, so this is the K method, and this K method has some variant or enhancement approach, in the sense that there are also some enhanced approach for this method. We have, for example, in Nostrum, for example, you have also a variant known as KE method, and E is for enhanced. For enhanced, in the enhanced method, we have another definition for the p variable, essentially, in the sense that we start by the same equation. We start by equation here, by the equation, this equation here, by this, and let me rewrite this asterisk equation. So by this, we have minus omega square, the flatter equation rewritten for implementing another variant, and so we no, excuse me, we have yes, we no, yes, we have this, and then we can multiply and divide this equation by the same quantity. We have again 1 plus g, so we can divide it by 1 plus g again, ig, excuse me, but we also consider this position. We want to multiply by u square infinite, u square infinite, and also a b square, and we therefore consider inside here what I already done for this part. I have here this part, which is equal to, remember, to 1 rho b square by k square. So this is 1/2 rho b square divided k square, instead of this, and again we have a reduced frequency here. We have a reduced frequency here. Oh my god. And so at the end we can recast the system in this way. We have minus u square infinite divided by 1 plus jg, and we can move this k square by b square inside, so we have k square by b square by the mass matrix, and here we have 1 on rho plus 1/2 rho, 1/2 rho, and so we can simplify this b square and k square here, so we have something like b square by k square, and we have a k square by b square, so we have this, and we have k Mach number, if any. If you have a Mach dependency. So let me move this dependency to simplify our vision. We don't have a Mach number dependency at the moment. And so we have simplified this part, and here we have a multiplication of all this part. We have divided by this, and so we have also a simplification for k here, but we can now introduce a p2 new variable as equal to minus u infinite to the power 2 by I plus ig, and therefore by this definition we have that p2 is I u infinite divided by square root of 1 plus jg. So we have this new definition, and after this new definition we have this, and we have again a k on b variable multiplied by p2 d plus k, and this is p2 to the power 2. So this is p2 to the power 2, and this is p2. So another variable similar to p1 is just another way for viewing our problem in a different manner, but the basic meaning is the same. Okay, so again you can plot your, this is the final result, you can plot your k as a function, you can plot your imaginary part of p2 to the power 2 and also the real part, but now the meaning of these two parts is different. We have this, we have a real part p2 squared like this, and if you see the meaning, just to conclude, you have that the meaning of p2 squared is minus u infinite u minus jg divided by 1 plus g squared. And so, just to conclude, we have that our real imaginary part of p2 squared is represented by real part minus u infinite divided by 1 plus g squared. Imaginary part is j g u infinite instead of omega like before, and so you have a similar criterion. In this case you have a critical value for your kappa flat is this, and correspondingly the imaginary part is 0, and then g is 0 as you want. Correspondingly the real part here is represented by minus u, so this is g is 0, and therefore this value is just minus u infinite. Before, that value was minus omega. So you have the k flutter, you have u flutter, and therefore you have also omega flutter, like k flutter by b u flutter. Okay, and this is the enhanced, is enhanced because in somebody proved that this way for iterating is more efficient with respect to the other one, and therefore this is known as k enhanced method. Okay, and we have concluded this part on the iterative. This is the most popular commercial iteration method for adding the flutter margin for aircraft. Okay, and so we can stop here. We can see the day after tomorrow for our lecture on afternoon. Have a good afternoon to everybody, and thank you for your attention.
Sorry, Professor. What kind of error we have between the K method and the PK method in evaluating the flutter condition?
No error, because you are in the imaginary axis working, and you are evaluating correctly your aerodynamic metrics on the imaginary axis, and so there are no approximation on fine. If you are converged in a value for your critical value, you are not doing any kind of approximation, but you are on the imaginary axis. You are not out of. You are not able to evaluate stable poles in any case, but only the margin condition.
Okay. Yeah, I mean between the two values that can be obtained by the two methods.
The two methods are equivalent. It's just a different way for implementing the continuation algorithm. In the continuation algorithm, you separate artificially two problems. You separate the rule of K with the rule of omega. This is the continuation method approach. Okay? And in this case, you do this and you introduce an artificial parameter like G. So at the end of this iteration, you want to suppress your artificial parameter at the end, and you want to relate your K value with the other value like omega and like U infinite. Okay? So whenever you are converged, you are not doing no error, because you have satisfied your characteristic equation and you have closed. You have satisfied because you have taken the determinant. You have taken the determinant for each iteration. You take the determinant for evaluating P. Whenever you evaluate P1 or P2, you have just performed your determinant. You are developing your determinant. So you are satisfied the determinant condition. And you have satisfied the fact that G does not exist and that K is equal to omega L by U infinite. So you have closed any kind of initial hypothesis.
Okay. And obviously the K method is more computational, cioè nel senso che è più leggero dal punto di vista computazionale, ovviamente.
No, entrambi molto veloci. Cioè, ormai oggi come oggi non è più come una volta. Stiamo parlando sempre, ricordatevelo, stiamo parlando di 10 equazioni, cioè il determinante di una matrice 10, perché stiamo in variabili modali, quindi prendiamo i modi. Avete visto quelle figure che avevo preso in rete? Così, manco l'avevo viste prima, ho scritto in rete una cosa, sono 10 modi, un'analisi con 10 modi quella.
Beh, certo.
10 per 10, non ci vuole niente a fare niente 10 per 10. E a trovare le equazioni, le 10, anzi le 20 a coppie, perché è un'equazione 10 per 10 con un P quadro, quindi quando fate il determinante viene 10 per 2, viene un polinomio di grado 20. Ok?
Quindi diciamo
13 sotto.
Sì, quindi diciamo che comunque pure allo stato attuale è sempre conveniente fare il metodo PK rispetto.
Diciamo che l'80% mediamente sento utilizzare l'80-90% dei casi il metodo PK e l'altro 10% il metodo K. Diciamo che il primo metodo che avete utilizzato voi per l'esercitazione numero 2, il metodo, quello che calcolava, vi ricordate, le equazioni b quadratica in U quadro?
Sì.
Non so se avete cominciato a lavorarci sulla seconda esercitazione. Quello è un metodo equivalente a questo, solamente invece che avere g, avete un quadro che sapete che è un numero reale positivo e quindi annullate la parte immaginaria. Quello è un continuation method, quello che abbiamo fatto per risolvere analiticamente l'esercitazione numero 2. È un continuation method che valuta solamente i valori marginali e lo fa non introducendo g come il metodo K, ma introducendo il fatto che un
un
finito
quadro deve essere reale.
che deve essere reale la parte immaginaria di un quadro. Cioè che non potete avere una radice complessa, perché non è complesso.
Sì, sì.
Va bene?
Va bene, professore. Grazie.
Prego.
Professore, scusi,
Sì.
ma quindi anche nel caso dell'esercitazione ci verranno due valori di U critica e la più bassa è quella che noi consideriamo come valore critico? Oppure...
Non ho capito. Certo, è sempre
Ok,
più basso. Quando studiate un carico critico, quando studiate un limite di stabilità di Flutter e avete un parametro che varia, è un parametro prestazionale del vostro sistema che aumenta, no? All'aumentare delle prestazioni del sistema, è chiaro che è il valore più basso quello che vi interessa, il valore è l'attraversamento che avviene, anche perché dopo quel valore, dopo nel senso uno immagina di aumentare la velocità, no? Dopo che il sistema è già instabile, che vi frega che ci sia un altro polo che attraversa?
ok.
Non ha senso, no?
Sì, 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 grazie.
È come il carico critico, trovate il valore più basso del carico critico, i valori successivi. Lei l'ha fatto con me costruzioni strutture aerospaziali?
Sì, sì.
Allora che gli frega che ci sia per una struttura un modo critico con 12 onde, no? Quando ce n'è un altro prima a 10, cioè si
Sì, sì,
sfascia
sì.
prima la piastra o l'ala o la struttura,
Ok,
no?
grazie.